pleasure to invite Ylva Ferstl from Trinity College.
I will be presenting the paper Multi-objective adversarial gesture generation, and I am Ylva Ferstl from Trinity College, Dublin. So our goal in gesture generation is we want to automatically produce speech gesture behavior like this for some input speech signal for virtual humans, obviously. And traditionally there have been three main approaches to solve this problem. First, rule-based approaches to just use hand-designed phrase-to-gesture rules to design a gesture, then statistical modeling approaches that use estimated probabilities between certain speech tags or certain gesture tags, and for that you need a large label-based data set to be actually able to model these probabilities. And then there are machine learning approaches, which ours counts amongst, and they are entirely data-driven. They've had varying success, and we use a generative adversarial network that we've already merged today, because they've shown great generated results in the computer graphics domain. And our work is the first work using GAN for generating natural conversational 3D gesture motion. So first of all, since our approach is data-driven, we need a data set, and we recorded 6 hours of just one native English speaker producing completely unrehearsed, spontaneous, natural speech, and we recorded very high quality 3D motion, the speech and the video. So you can see an example here. So just a quick starter of what GAN is. I'll go over this quickly. We've already heard about them today. So in a standard regression training, as opposed to a GAN, we would have here the input signal, which is a speech signal. Then we have the generator who generates our output, in our case some poses, some gesture motion. And we have on the other side the real data, and this is then compared directly, for example, the mean squared error of how this output is wrong. And this is the feedback to the generator. So the generator gets this exact training error of how its output is wrong. So now a problem with this is that, especially in gesture generation, there's multiple true answers of what would be a valid gesture. For example, if you look here at the output and the real data, the last pose would just be the mirrored pose, and that would lead to a very large mean squared error, but they would both be valid answers. So because this is such a difficult problem to learn, you a lot of times have the problem of mean pose convergence, where the generator ends up just producing some lethargic motion around the mean because it minimizes the error across all possibilities and it's just not able to do anything else. So now on the other side we have GAN training. So instead of using a regression error, a mean squared error, we train a second network called the discriminator, that says whether the motion looks real or not, and that is the training feedback to the generator. So it's a very indirect, yes, you got away with it, or no, you did not get away with it. And the discriminator is jointly trained with the generator, on our case just on a standard classification task, so it learns to categorize motion as either real or fake. So this is a much more indirect feedback to the generator. It is only getting told, yes, the output was okay or it was not. It does not get told how its output was right or wrong. So it is, you won't have the problem of mean post convergence probably, but it is also very hard to train with this error. It takes a long time because it's just, the generator has to just search around in the dark a little bit. Okay, so let's take a quick overview of our system specifically. We will have an input speech signal, a generator that produces our gesture motion, and then on the bottom here, we'll go through it step by step. We have multiple evaluation aspects, how we want to evaluate the output of the gesture motion. And each of these evaluation aspects that we will look at is represented by one discriminator, so one adversary, and in the sense of a generative adversarial network. So we'll go through it step by step. So first, let's look at our generator. We have a speech input signal that is just automatically extracted speech features. And then we have a standard kind of recurrent network that can handle sequential data. So recurrent networks can handle time series data. In our case, the time series is 5 seconds of input speech, and output is the concurrent 5 seconds of gesture motion. And each predicted frame of that gesture motion is dependent on the previous frames, so that there's a continuous sequence. And then our output are the X, Y, and Z positions of the 21 joints that you can see here. So they're the 5 joints of the spine and 8 each per arm. And now we'll start breaking down the evaluation of this output into our multiple sub-problems. So our first type of problem is we want to model the characteristic dynamics of gesture motion, which is not that easy because gesture motion is not this continuous kind of motion that the generator might learn to predict. And gesture dynamics can be described by so-called gesture phases. So what are these gesture phases? A gesture usually starts with a preparation where hands come into position. Then there might be a short hold before and after the stroke that carries all the emphasis and the meaning of the gesture. And then there could be a partial protract before the hand starts doing something else, or a full protract before the hands then come back to their rest position. And these phases that you can see here and just described, they're, besides the stroke phase, they're all kind of optional, and they can have it can be a much longer sequence from one preparation to the next rest. So they're not easy to predict or to model. Gesture motion is very fast and very variable. So if we want to implicitly model all these dynamics, the gesture phases, we would probably need lots of data to train on and just kind of hope that the generator will eventually get it. Or if we want to explicitly model these gesture phases, so if we want to judge all our motion on the gesture phases, then we need gesture phase labels, both for all of our training data and for new generated data that's being constantly produced in the training. So we need some on-the-fly phase labeling because any new output needs to be evaluated on its gesture phases. So we need to do this automatically, so we train a phase classifier. But this is also difficult because, first of all, we need a lot of data to train this phase classifier on, which is tedious to collect, just annotating, for example, 1 minute of gesture motion with its phase labels takes an experienced annotator a full hour. So 1 hour for 1 minute of data. And also there is not one true label, so the same experienced annotator might look at the same clip of gesture motion, do it twice, and label it differently. So previous work for that reason has often focused on either just segmenting one gesture unit, so from one preparation until the next rest, or just labeling the emphatic stroke phase. But we want more than that. So we trained first a set of annotators to annotate 226 minutes of our data set that I showed in the beginning using the pictured phase labels. And we'll not go into the network details, but it is another recurrent network that receives as input not the exact joint positions, but how much each joint moved in each frame, and it says for every frame what phase label it thinks is happening right now. And we use the annotation tool ANVIL. Sorry, that's a bit cut off here. If you can see here. So let's look at the results. After experimenting with a different number of phase labels, we decided to use just 4 phase classes in our training. So we group all hold, so the hold before the stroke and after the hold into one label as hold. And we group the very rare phases into one class other, because note that for our speaker, at least, the partial retract and the retract are very rare. The retract only happens less than 2% of the time. The partial retract, which is only like a very short backward motion, only less than 4% of the time. So it did not make sense for us to penalize the generator if it is producing these very rare phases or not. So this is all just being grouped into the other phase. So in the video here, you can see real motion that the classifier has never seen before, and that it is automatically assigning a phase label. So this is what the, it's showing the 50% speed so that you can see this is what the classifier thinks is happening. And now that we've trained this classifier, we will use it as a static, unchangeable component in the whole system. So we will use its output as the ground truth. We just assume that whatever the classifier thinks the phase label is the phase label. And its output will be the input to our first discriminator, our first adversary. So our first adversary is the phase structure discriminator, and it receives as input such a sequence of generated phase labels from the classifier, and like a standard discriminator, it just says yay or nay, I think this is a real sequence, or I don't think this is a real sequence. So to see the effect of this discriminator, we can take it out of the training and train the network a bit without it. So the idea is that it enforces our realistic gesture dynamics with strokes and holds. And when we take it out in the video, I'll play it in a minute, but as audio, we can see that the motion shows no clear holds or accelerations characteristic of the stroke phase, and the motion appears to also correspond less with the audio.
So growing up, my mother always wanted to kind of give us equal opportunities in relation to different art forms that we should take with us into and kind of add to it. And one of the things that she kind of always made sure that she wanted us to kind of be able to do it.
Okay, it's back. Now we still have the problem if we just train our generator between our first discriminator, just with the error from the first discriminator, that the generator can get away with just random point clouds because the classifier will always assign some phase label because it's automatic. That's all it can do. It can assign a phase label, and the discriminator will only see that phase label. And then the generator will diverge. It will not just like implicitly stay around the skeleton structure. It will just learn to generate something. So something like this can happen, which are producing these rhythmic point clouds that trick the classifier basically. And the discriminator, the phase discriminator, has no way of saying whether this is real motion or not. So we need to add a second discriminator, the motion realism discriminator, that looks at the actual output of the generator, the actual produced joint positions, and says whether this looks like a real input or it doesn't. And it also gives this motion realism discriminator the same input as the generator, which is the speech signal, so it can also look at the correspondence of this generated motion to the speech signal. Okay, so now the motion realism discriminator that I just presented now, such as any standard discriminator, is really only designed to not look at one sequence at a time of the output. And this can lead to so-called mode collapse, where the generator produces the same repetitive pattern of motion and always just slightly shifts this pattern once in the next training iteration. The discriminator learns that this exact sequence is fake, so something like this can start happening where, yes, it looks like motion, real motion, maybe if you want to look at 2 seconds of it, but then you realize that it's very repetitive. So we can add a special mini-batch discrimination layer that calculates a mini-batch similarity, so the similarity of all sequences in one batch. So the generator will never get away with producing the same or similar pattern, reproduced throughout the batch, because then the similarity will always be high. We could include this mini-batch discrimination layer in the motion realism discriminator that I just presented, but we just find the training to be more stable to separate it into a third discriminator, just train as a third. So then what I didn't mention due to the time constraints before, you can ask me later or read it up in the paper, we actually did have to pre-train the generator with the standard regression loss with the mean squared error. For reasons relating to the automatic phase classification that cannot handle random point clouds. And this leads to the expected mean post convergence. So at the beginning of the training, the generator is slow to move away from this lethargic motion around the mean post. So we add a side objective of a joint displacement discriminator that receives just how much each joint move in each frame to say it's not moving enough, and then the generator will be faster to move away from this mean post. It will eventually probably move away from that mean post, but it will take a long time, and GANs take a long time to train anyway. So as I said, it receives the joint offset per frame, but note that this is also actually the same input that the phase classifier receives. So they are kind of phase structure discriminator and our discriminator here now, the joint displacement discriminator, are somewhat related. So for fair comparison, we can also take them both out and see what the motion would then look like. So eventually, after we train longer, it moves away from the mean pose. The dynamics are kind of unrealistic. It moves slightly too fast. It's a bit jittery. And if I played audio, you would also see that it does not correspond well to the speech. So then we have all of our training objectives. And we group them together to one joint error. So the generator does not receive 4 different losses, 4 different errors. It's just all of the discriminators are weighted, and that is one joint training signal to the generator. Then we also add 2 objective loss penalties that we just compute algorithmically. So the first is the continuation loss, because each discriminator is just concerned with how one sequence looks, but it's not concerned with how these sequences connect within the batch. So we just calculate the distance between one sequence and its previous sequence to calculate how well they connect, and add that as a penalization. And then we also introduce the finger distance loss, because note that the finger joints make actually up almost half of the markers. So it's actually really important for the overall error, but they're very difficult to learn. So we find that the generator converges faster if we restrict the finger positions just to realistic ranges based on the wrist position, so just so they don't fly up into space. Okay, so let's look at the results.
So growing up, my mother always wanted to kind of give us equal opportunities in relation to different art forms and that sort of stuff to take with us into kind of adulthood. And one of the things that she kind of always made sure that she wanted us to kind of be able to do and take with us was to play music. So initially we started off playing piano, which to me now, like looking back, I regret stopping. But sorry.
So we find a definite advantage of the adversarial training because we don't have the start problem of the mean post regression, but we also find that through this very indirect feedback, there's a little bit of a search in the dark for the generator. And we find the results promising, but I think we think they can still be much improved. It's just a very complex problem, and just the yay or nay feedback from the discriminator is maybe not enough for the generator to learn this complex output. And this is the reason we also didn't do a perceptual task yet, because we think you can still clearly see that it's not real motion. But we want to find out first, like, how can we actually, what is so important in gesture motion, what makes it look so characteristic, what other feedback do we need to give to the generator for it to look more realistic. So we find standard regression loss too constrained, but also the GAN loss may be a little too unconstrained, and we want to look into further ways to improve this modeling. We do see a benefit to the subproblem definition, as you can see when you take out certain discriminators, and we also rely less on modeling all aspects of realistic gestures. And GANs are notoriously hard to train, and we find the training much more stable by introducing more discriminators. And also in the future, we want to understand and model gestures better by looking at different speaker styles, different personalities, looking how gesture is affected.
Did you have a chance to compare with other based gesture generation methods?
Our initial work was just on standard recurrent networks, but we just find that in our work and also in some related works that use this approach, the motion is not very expressive. It does stay a lot around the mean pose. It doesn't have these very characteristic dynamics. Often seems a bit slow and just not as expressive.
have time for one more question. Anyone?
Thanks. So as you get more data from other speakers, how do you differentiate between the classifier choosing what is based on style and what's more of a general gesture phase?
Do you mean for the phase classifier specifically, or? Yeah, that's actually a difficult problem. So we have another data set from a very different kind of speaker who moves much more fluidly. A lot of his motion is just the whole body motion, and we tested our classifier on that. And it's kind of good. It's it's not great, but it gets some phases. But certain things like holds that are very static in the data set we were trained it on, and then very fluid in the other data set, they will be difficult to predict. So things like a very emphatic stroke phase can still be detected well. Holds depends. It does depend on the speaker. So we would like to be able to model more speakers for phases as well.
We have time for one last question.
Have you considered inputting other information than just the pure speech? For example, using segmentation for that to see what the person is actually trying to sell or which words it's using, like for example, focusing off these repetitive words that I try to explain something or focus on nouns and stuff.
No, definitely, yeah. We looked into that a little bit and we tried just to find the most common keywords and things like that, but it's very difficult if we don't have a huge data set because, for example, if you look at any semantic network, anything like a word recognition network, they are trained on hundreds of hours of speech just to be able to model the very direct relationship between speech input and the text it corresponds to. And still it takes so much training data. So with our 6 hours of data, unless the speaker keeps talking about the same thing and doing the same gesture for it, very little chance of being able to get really explicitly semantic meaning out of it. So yeah, we need more data.
Let's turn to the speaker.